So before I proceed with this afternoon session, are there any questions with regard to the material that I presented last time, or that you see in your notes? You see in the notes from Ugle. Any questions?
Sir, pwede po pa-explain further yung energy band diagram kasi medyo nakakalito po siya.
What in particular sa energy band diagram?
Sir,
How it was derived?
Opo, sir.
Sige. Okay. So, naintindihan niyo yung ano, no, yung shells, yung sinasabi nating shells, yung maybe yeah, okay. So, yung silicon, doon sa outermost shell, okay, you have two s electrons, and then you have two p electrons, no? Doon sa outermost shell, no? But there are actually 8 possible electron states. Okay. Ngayon kung yung electrons, kung yung mga atoms natin malayo from each other, if they are far apart, they don't really interact with each other, and two electrons can have exactly the same electron state, no? So if I plot, for example, these are your possible energy states, no? E is your possible energy states, and then this is distance x. Okay, let's say at this distance, this is electrons very far apart, or not electrons, atoms, no, sorry. Atoms very far apart. Yung electrons mo can exist in the same energy state, no? So we can have here what we call discrete. These are called discrete energy states. So you have 2s2 and you have 2p2. Ngayon, kapag malapit na yung mga atoms mo, no, the electrons in the valence band, no, in the outermost shell, start interacting with each other, no? It starts forming what is called an S system. And when that happens, because of a principle called Pauli's exclusion principle, which says that no two electrons in an electronic system can have exactly the same state, nagkakaroon ng splitting, no? Nagkakaroon ng splitting. Okay? So you have what is called your band splitting. Splitting of your energy states. So yun ang nangyayari dito, no? So from this discrete energy states, nagiging energy bands. For a while, it looks like walang distinction between yung 2s and 2p, no? But at some point, no? At some point, this will split into two, no? It will split into two. So dito sa point na to, buo pa siya, it is just one continuous energy band. But at some point, this will split into two, no? And if you get this is the normal distance between your atoms in a solid. So this is going to look this way. So ito, no, itong normal distance of the atoms in a solid. If I expand this part, ito yung energy band diagram. Yun yung tinatawag natin yung energy band diagram. So actually, ini-expand lang natin itong part na to where the distance between atoms is the normal distance between atoms in a solid. So if I expand this, ang magiging itsura niyan, parang ano no, parang binlow up ko lang to no. Itong part na to, parang binlow up ko lang na paganon. I just widened it to as wide as possible. Magiging itsura niyan parang ganito. No? Where I call this my conduction band, and I call this my valence band. And then E of C is the smallest possible energy for a conducting electron, and E of V is the largest possible energy for a valence electron. Okay. Your valence electrons are what makes up a solid. Teka, so far, naintindihan mo pa? Did you understand it or malabo?
Yes, sir. Nakakuha ko.
Okay. So actually, yung energy band diagram, parang binlow up lang natin itong portion na to, no? Where this is the part where your energy level split. No? So pag malayo-malayo yung atoms, pwedeng pare-pareho yung value nila, no? Pero pag malapit na yung atoms, hindi pwedeng pareho yung mga values ng energy states ng electrons. Kaya nag-i-split siya into what is called bands. And for a while, parang walang distinction, no? Pero at a certain distance, nag-i-split into two. You have what is called your conduction band and what is your valence band. Ano? Sorry. Okay. And so ito, i-blow up natin to. Ito yung magiging itsura. Okay. And this is what bonds, itong electrons in the valence band, this is what bonds your atoms together in a solid. Okay? Ngayon, pag dino-drawing siya, since this is energy, usually this is taken as the reference, no? Parang ito yung ginagawang reference. Kasi energy naman yan, no? So you can have any reference. You can make this as your zero reference. But actually there are energy states here that belong to the atoms that are closer to the nucleus. Yung from the one shell and the two shell. Ang pinapakita lang dito is from the three shell in silicon. Are there any other questions? No? And then I explained earlier that this is what you call the forbidden band. There are no energy states between EC and EV. At least for a semiconductor. For a conductor, nag-overlap yung dalawa. For an insulator, yung forbidden band is very, very large. And then for a semiconductor, this is about 1 electron volt. Okay, I'll just do a short recap of what we discussed last time. If you have any questions, please interrupt me anytime. If there's something that is not clear, wag kayong mahiyang magtanong. I don't find any question stupid, no? In fact, by asking questions, even if it sounds like it's a stupid question, you might be doing your classmates a favor because maybe they also are wondering what the answer to that question might be. Okay, so last time, okay, this is just to summarize, we talked about intrinsic semiconductors. Intrinsic semiconductors are what we call pure semiconductors. No? Pag sinabi nating pure, ibig sabihin walang hinalo rito sa element na to. No? All the atoms, for example, in an intrinsic silicon semiconductor, all the atoms would be silicon. Nothing is mixed with it. So we said that the most common semiconductor material used in electronic devices now is silicon. This has 14 electrons. So we said there are 4 valence electrons, but there are 8 possible electron states. So this is a two-dimensional representation of the silicon solid. It is a crystalline structure. So pag sinabi natin crystalline, ibig sabihin, the nuclei are arranged in a pattern, no? in a repetitive pattern. The actual pattern is 3D, it's tetrahedral, but here I'm just drawing a 2D representation. So here I'm showing you that each silicon will have 4 valence electrons. So dito, you see the 4 blue electrons surrounding the blue silicon atom. And these 4 electrons are shared with 4 other silicon atoms. No? So this is shared with this is shared with this, and so forth. No? This is shared with this, and so forth. No? So that from the perspective of each silicon atom, it looks like there are 8 electrons surrounding it, no? Or 8 electrons in the outermost shell. No? That's what it looks like, right? But actually, only 4 of those electrons belong to it. No? The 4 are shared with 4 other silicon. And when you take a look, those 8 now satisfy the 8 possible electron states, existing in the third shell of your silicon. Okay? And that sharing is actually what binds your silicon atoms together. That's why you call it a bond. No? Ito yung pamamaraan nila para mag-bonding sila, no? Okay? So that is what forms the solid, these covalent bonds. Okay? So each covalent bond consists of a shared atom between 2 adjacent silicon atoms, shared electrons between 2 adjacent silicon atoms. Okay, so again, this is our energy band diagram. So this is a blow up of that portion of your energy diagram at the interatomic distance. Okay, the distance between, or the gap between your EC, this is the smallest possible energy of a conducting electron, and EV, that is the largest energy of a valence electron. Okay, that difference is about 1 electron volt. This is for silicon. At 0 degrees Kelvin, the valence band is full. In other words, all the electrons exist here. So nandito yung mga electrons natin. Nandito yung mga electrons natin. I'll just draw it this way. Okay. Now, at greater than 0 degrees Kelvin, it is possible for a number of these electrons to acquire what is called thermally acquired energy, to get thermally acquired energy. And because of that, it might be possible for an electron here to be promoted to the conduction band. No? In other words, at a temperature greater than 0, itong, for example, itong electron na to, no, posibleng ma-promote dito. So what will happen then? Okay, so let's say this is promoted. So you now have an electron here, and what you have here is what is called a hole. So we call this a hole. Okay, what will happen if I apply an electric field? So let's say I apply an electric field. So let's say this is my electric field.
Sir?
Yes,
Sir, I have a question po. Can you repeat the po? What's the meaning of 1 EV there? Between EC and EV po?
1 electron volt. That's energy. No, energy. Energy is joules. Remember energy? That's joules. Okay. What is volts? Volts is joules per coulomb, right? And E is the charge of 1 electron. So one EV is a unit is actually a unit of energy. EV, saan ko isusulat yun? EV, this is a unit of energy. No? Because E is the charge of an electron, and then V, by definition, if you recall your triple E 1, 2, 3, this is joules per coulomb. No? Now, the charge of an electron is in coulombs, so you multiply E times V, ang lalabas niyan is joules. So we use electron volts when we in semiconductor physics, no? Because if we use joules, the values are too small, masyado maliit, no? For example, the charge of an electron is 1.02 times 10 to the minus 19 coulombs, right? So we will be dealing with very small numbers if we use joules. That's why in semiconductor physics, usually we use electron volts. Did that answer your question?
Yes po, sir. Thank you po.
Yeah, I hope it did, no? Okay, so going back here, no? So pag mas malaki sa 0 degrees Kelvin yung temperature, yung electron na rito might have enough energy to get promoted now here to in the conduction band. So if I apply an electric field, let's say my electric field is right to left, where would I expect this electron to go? Will it to move left or will it move right? Can somebody shout out an answer? Saan siya pupunta? Kung naka-experience yung electron, which is a negative charge ng electric field, will it move left or will it move right? Anyone?
Sir, left po.
Right
Left?
po.
Okay.
Right po.
Okay, I hear more rights than left. Actually, the correct answer is right, no? Remember that an electric field tends to push away positive charges and tends to attract negative charges, no? So the electron, sorry. The electric field will push positive charges. So if your electric field is left to right, your positive charges will move to the left, no? And the source of the electric field will tend to attract negative charges, no? The source of an electric field usually is a positive charge. It will tend to attract negative charge. So your electron will move to the right, no? So itong electron na to will move this way. Okay. Ngayon, itong electron na to is bound. It is bound, no? It is one of these electrons that is bound to the nucleus, bound to the nucleus of the atom. It will not have enough energy to move here in the conduction band, no? But because of the electric field, this electron might be able to move here, no? Because it does not need additional energy to move to that particular hole. Remember, we created a hole, no? When for example, when this electron, hindi nag-work. Now, anyway, no. Let's say, for example, this electron. Let's say this electron becomes promoted to the conduction band. Nagkakaroon ka ng hole here, no? So this electron will not be able to move because it does not have this amount of energy, but it's possible that it will move into this hole. So ngayon, ang mangyayari, okay, my electron now will be here, and where will my hole be? My hole now will be here. No? So this is now going to be my new hole. And so forth, ano? Pwedeng ganyan, no? And then again, I have a new hole here. No? Okay. So my hole will end up being here. So ang hole it looks like my hole is moving to the left. No? That's why we say the hole acts like a positive charge carrier. Okay, why is it like a positive charge carrier? If this is my hole, no? For example, if this is a hole, no? If this is a hole, sabihin natin hole yan. Okay. I have enough positive charges in the nucleus to neutralize 4 electrons. But I only have 3 electrons around. No? This can neutralize 4 electrons, but I only have 3 electrons around because this is a hole. Which means to say, if I take a look at this particular structure, no, this particular part of the solid structure, it is positively charged. Kasi mas madaming positive charge sa nucleus kaysa sa electrons surrounding the nucleus. So habang lumilipat yung hole, para lumilipat yung positive charge. That's why we say the hole acts like a positive charge carrier. By the way, when an electron is promoted, so earlier we said this electron was promoted there, we create what we call an electron hole pair. In other words, in an intrinsic semiconductor, in a pure semiconductor, every time you create an electron, a free electron in the conduction band, you also automatically create a hole. So that's why your electrons and holes are always created in pairs in an intrinsic semiconductor. So we have the definition intrinsic concentration. This is N's of I. This is the number of conducting electrons present in a pure semiconductor at a particular temperature. And for silicon at 300 degrees Kelvin, okay, last lecture I mentioned that this was 1 times 10 to the 10, but in your reference book, the figure they use is 1.5 times 10 to the 10. No? So different references will use different figures. Actually, even if you take a look at the graph that I showed you last time, it wasn't exactly 1. It was really greater than 1 dun sa graph na pinakita ko sa inyo. No? So that's how we're going to use this. No? 1.5 times 10 to the 10, also to be consistent with the notes that were published in UVLE. Okay. If N is your electron concentration, and whenever I say electron concentration, I'm referring to free or conducting electrons. I'm not talking about electrons in the valence band. I'm talking about electrons in the conduction band. So if N is my electron concentration and P is my hole concentration, for pure silicon, N will always be equal to P because they are produced in pairs, and that will be equal to my intrinsic concentration. Take note that silicon has 5 times 10 to the 22 atoms per centimeter cube, per cubic centimeter. That means that I'm only generating 1 electron hole pair for every 3.3 times 10 to the 12 atoms. So that's how few electrons are promoted to the conduction band at room temperature. That's only 1 electron hole pair for every 3.3 times 10 to the 12 atoms. Are there any questions so far? Any questions? Okay. So
Sir?
that's, yes, please.
Sir, may tatanong lang po. Pwede po pa-differentiate ng electron state and energy state? Medyo nalilito lang po.
When I say that this it's the energy state, yeah, the energy state is actually the state of the parang placeholder, no? Placeholder ng electron, no? Actually, I use the term interchangeably, no? The energy state of the electron, no? Kasi for example, no, kung yung valence electron natin is unoccupied, there's a particular energy state associated with that unoccupied valence electron. There's a particular energy state associated with that. No? So the electron has to have that electron state to be able to occupy that slot, that particular slot. Medyo nakakalito ba?
Bali sir, parang yung energy state po, siya po yung slot and then si electron state, siya po yung mag-occupy ng slot. Tama po
Oh,
ba?
parang the electron has to have the energy corresponding to that particular slot to be able to occupy that slot, basically, no? In other words, kung yung for example sa conduction band, talk about the conduction band dito, no? For the electron to be able to occupy a place in the conduction band, it has to have this amount of energy, right? But the energy state here is only this much, so you have to impart enough energy for it to be promoted up here. Kailangan dagdagan mo siya ng energy. Now, how do you do that? One way is by heating, by heat, no? And then there are other ways which we're going to learn about later on.
Understood po sir. Thank you po.
Okay. Yeah. Okay. So let's talk about extrinsic semiconductors. Medyo mabadaliin ko lang ng konti, ano? In extrinsic semiconductors, impurities are added to enhance the electrical properties. To enhance the electrical properties of the semiconductor. So impurities are added. Pag dinagdagan natin ng impurities ng semiconductor, we now call it a doped semiconductor. The process of adding impurities is sometimes referred to as doping the semiconductor. And there are two types of impurities. We have what we call acceptor impurities. Tapos meron din tayong tinatawag na donor impurities. Okay, so let's discuss acceptor impurities. Acceptor impurities have 3 electrons in the valence band, in the valence shell. So typically this is group 3 of the periodic table of elements of chemistry, group 3. So examples of this would be boron, aluminum, and gallium. No? Those are, pag tinignan nyo sa periodic table, those are elements in the group 3. Okay. Now, when you dope the semiconductor, and your notes will describe processes for doing this, ano? There are different ways of doping a semiconductor. You do it through diffusion or ion implantation. Basta may mga processes yan. It's not that important for you right now, but I think there's a briefing on that in the notes. Ano? When you dope a semiconductor, what happens? The impurity will take the position of one of the atoms of silicon. So for example, I have I'll show you again my solid, no? So let's say these are the atoms in my solid silicon. Let's say this is silicon. These are all silicon. Okay. When I dope it, let's say I dope this with boron, no? One of the silicon will be replaced with boron. Okay, so you have the sharing of electrons, no? So nag-share ito ng electrons, right, in the covalent bonds. Ang problema, ang boron, tatlo lang yung electrons niya, no? So ito will not be able to share an electron with one adjacent silicon, no? Itong itong electron na to, ang pagmemay-ari niyan itong silicon, ano? Itong boron walang mai-share dito sa silicon na to, no? Because it only has 3. It only has 3 in the outermost shell. So immediately you have a hole. Immediately there's a hole existing. There's an empty energy state existing here. Because this boron has only 3 electrons that it can share with 3 other silicon. So yung isang kapitbahay niya, hindi niya mabibigyan ng electron. If I take a look at the energy of that hole, so again, going back to the energy band diagram. So this is EC, EV. Yung energy ng hole na yan will be somewhere here. No? I'm just going to draw it as a line because it's a discrete energy level. It is not a band, no? Because konting-konti lang yung concentration ng impurity, so it will never split into bands. It will stay as a discrete energy level. No? So this is the energy level of the hole introduced by doping. Okay. Ngayon, yung electron na nandito, posibleng kulang siya ng energy para tumalon dito. No? Let's say meron tayong electron dito, posibleng kulang siya ng energy para tumalon dito, but it might have enough energy para tumalon dito to occupy this particular hole. So ito, pwedeng tumalon dito. Okay. So I now have an occupied hole here. Okay. Pero ngayon, dito sa regular lattice structure ko, meron yung silicon that will have 1 missing electron and therefore lumipat yung hole. So for example, baka ito, posibleng ito tumalon dito. So this will go here. Okay. And now I will have a new hole. Sorry. So now I will have a new hole here. No? So this will be occupied and then I will have a new hole. So again, in the presence of an electric field, it might be possible for electrons now to keep jumping from hole to hole. No? So yung normal mechanism ngayon babalik. Okay, so that is your acceptor impurity. Any questions with regard to that?
Sir?
Yes,
Yung question lang po tungkol po dun sa energy level ng hole introduced by doping.
Yes.
So hindi po ba yan po that falls under yung forbidden
Yeah,
energy? Yeah.
The forbidden energy band is for a pure semiconductor, no?
Okay po.
For an intrinsic semiconductor, you cannot have any energy levels between EC and EV. No?
Okay.
But when we introduced this particular impurity, we introduced an energy level that is just slightly above EV.
Okay po.
So that yeah, but it's a good question. Thank you for asking that question. No? You now can have that energy level because of the impurity that was introduced.
Okay po. Thank you, sir.
Okay. Okay, so yun yung acceptor impurity. So anong tawag dito? Ang tawag dito sa semiconductor na to, this is called a p-type. A p-type semiconductor. And the reason why it's called a p-type is because P now is going to be greater than N. P is your hole concentration. N is your electron concentration. Okay. Your hole concentration now is going to be greater than your electron concentration. Sorry. Okay. And so it's called a p-type. Nawala yung p-type ko. Now, does that mean that this is positively charged? Anyone? Is this going to be positively charged? I don't mind a guess. I don't mind you people guessing. Yes, if you think it's going to be positively charged, give me a thumbs up. I just want to see. Okay, I'm glad that somebody had or some of you have the guts to answer. No, unfortunately, sorry, no, it's not going to be positively charged. Okay, the reason for that is itong boron atom na to will have enough positive charge in the nucleus to neutralize 3 electrons. Right? So by itself, it's neutral. No, the boron atom will have enough charge in the nucleus to neutralize 3 electrons. By itself, it's neutral, and all other atoms will also be neutral. So in totality, this whole thing will be neutral. The fact that it has more holes than electrons does not make it positively charged. No, it's just that there is more opportunity for current to flow, but it does not make it positively charged. So that's your acceptor impurity. No? And then the other type is your donor impurity. And yung donor impurity mo naman has 5 valence electrons. So this would be group 5 of your periodic table. So for example, phosphorus or arsenic, these are examples. And I think you can already guess, if this is your solid, if this is phosphorus, this is silicon. Okay, you have silicon here, you have silicon here. Okay, so your phosphorus will share 1 electron with each of its 4 neighbors. But after sharing 4 electrons with 4 neighbors, meron pa siyang isang extra. You have an extra electron. So there's an extra electron associated with this particular phosphorus. Dahil sa 5 yung valence electrons niya, no? It belongs to group 5. Now, is this going to be negatively charged? No, it's not going to be negatively charged because this phosphorus atom has enough positive charge in the nucleus to neutralize 5 electrons. No? So this is not going to be negatively charged. But the fact is it will have an extra electron. No? And where is the energy of that electron? Again, if I take a look at my energy band diagram, this is EV and this is EC, the energy of that electron will be somewhere here. This is the energy of the extra electron. Okay. And therefore, it takes very little energy for this electron to jump into the conduction band. Kung nandito siya, madaling-madali siya makakatalon dito, no? Konting additional energy lang, maybe from heat, from ambient heat, makakatalo na siya dito sa conduction band. No? Thereafter, it is already a free electron. It can roam around the solid. If you apply an electric field, it will move opposite the direction of the electric field. And this is now what you call an N-type semiconductor. Okay, the typical impurity concentration is about 10 to the 15 impurities per centimeter cube. If you recall, we said that silicon has 5 times 10 to the 22 atoms per centimeter cube. Okay, so if we do the math, this means that you have 1 impurity for every 5 times 10 to the 7 atoms. 1 impurity for every 50 million atoms. What is the significance of that? The physical properties of your silicon, let's say we're talking about silicon, will not change. Hindi magbabago yung physical properties. Bakit? No? Dahil for every 50 million atoms, isa lang. No? Isa lang yung ma-replace. No? Only one will be replaced by an impurity for every 50 million atoms. In other words, if I take a look at a doped semiconductor and a pure semiconductor, no, and an extrinsic and an intrinsic, they will look exactly the same. They will feel exactly the same. They will taste the same. They will smell the same. You will not be able to tell the difference between the two. The only way you will be able to tell the difference between the two is if you measure the conductivity or the resistivity, because one will have a lot more charge carriers than the other. But in terms of the physical properties, they will be the same. In fact, no, I mentioned this to my previous class. Kung ikaw si atom man at pumasok ka dun sa loob ng solid, no, siguro buong buhay mo hindi mo mahanap yung isang impurity, no? Because you're going to have to go through 50 million before you find one impurity. Okay? So that's how doping happens. No? That's how doping happens.
Sir,
Yes,
can it have both acceptor and donor impurities?
yes, it can. No, it can. The point is it going to be useful? The answer is sometimes. No. Later on, you're going to find out. For example, in a p-n junction, one side has acceptor impurities, the other side has donor impurities. Okay. So I said, no, the electrical properties will significantly change. Now, how will I illustrate that? Okay. So Ni, sabi natin, Ni at room temperature is equal to 1.5 times 10 to the 10. These are free electrons per centimeter cube. No? This is at room temperature. And room temperature, just for convenience, we just say it's 300 degrees Kelvin. That's actually 27 degrees centigrade, which is a little bit cooler than room temperature in the Philippines. Okay. Now, let's say we have an N-type, no? Okay, say we have an N-type. We say Nd is the donor impurity concentration. Nd, yun yung ginagamit nating donor, parang variable for donor impurity concentration. So sinabi na natin, let's say this is 10 to the 15 impurities per centimeter cube. No? Now, if we assume what we call total ionization, that means that all impurities are ionized. No? In other words, if it's a donor impurity, all the extra electrons will leave. No? Yun yung na-ionize siya. All the extra electrons will leave. If it's an acceptor impurity, all the holes will be occupied. So that's also a form of ionization. No? So if we say total ionization, that's all impurities are ionized, then the total free electrons after doping will be equal to Ni plus Nd. It will be equal to Ni plus Nd. Ni yun yung intrinsic concentration, yun yung impurities na nandun na if it was pure. Okay, I'm just going to say approximately equal, no? Because there are other things that will happen that might affect the value of the concentration. But the total free electrons will be, let's say, approximately equal to Ni plus Nd, no? But Nd is very much greater than Ni, so this is going to be negligible. Okay, if you compare 10 to the 15 by 1.5 times 10 to the 10, okay, that is the new concentration of electrons will be 60,000 times greater than the original. So yung bagong concentration of electrons will be 60,000 times greater than the original. Okay, so that is the effect of just one impurity for every 50 million atoms. Ang concentration natin ngayon of free electrons increased by 60,000 times. So that is the beauty of semiconductors. Without changing the physical properties and by just doping the semiconductor, we vastly change the electrical properties.
Sir,
Yes,
may tatanong lang po, bakit po natin kinancel si Ni po?
Because Ni, no, 1.5 times 10 to the 10, Nd is 10 to the 15, parang negligible lang. Hindi kinancel, negligible, no? Neglect.
Okay
In
pa.
other words, pag kuha ka ng calculator, i-add mo ito tsaka to, malamang lalabas sa calculator mo, ito din yung sagot mo eh. No? That's all, no? Okay? Okay, remember, no, for intrinsic semiconductors, N is equal to P, which is equal to Ni, no? Okay. Now Np will be equal to Ni squared, no? Itong formula na to, okay, that follows from here, no? N is equal to P is equal to Ni, or Np is equal to Ni. This formula happens to be true also for extrinsic semiconductors. No, and this is what is called the mass action law. Now, ano lang, intuitively, no? Intuitively, bakit nagiging totoo to, no? If for example, I have an intrinsic semiconductor and then I add donor impurities. So ang mangyayari, if I add donor impurities, nagkakaroon ng extra electrons. Kapag nagkakaroon ng extra electrons, there is a higher probability that these electrons will neutralize some of the holes. We call this, we have a term for this, we call this recombination. No? Posible na yung electron, yung extra electron, will combine again with the hole and form a neutral particle. So pag nagdagdag ako ng donor impurities, the natural tendency would be for the value of P to become lower than Ni. In the same way, if I add acceptor impurities, the natural tendency will be for the value of N to be lower than Ni. So nagkakaroon ng parang compensation by doping the semiconductor. We actually affect the value of the parameter that is not supposed to be affected by the doping, no? In other words, acceptor impurity, na-affect natin yung value ng N. Donor impurity, na-affect natin yung value ng P. And it will always turn out that the product of N and P will be equal to Ni squared. Yun yung mass action law. Okay, now remember what I said, that the semiconductor material is neutral. No? Is neutral. No? Kahit na linagyan ko yan ng donor impurity or acceptor impurity, it will not make the material either positive or negative or positively charged, because there will always be an equal number of positive charges in the nuclei, no, to compensate for the electrons. Okay, how many electrons will there be? Okay, how many electrons will there be in the solid? No? In the solid, the number of electrons per cubic centimeter would be equal to N plus Na, where Na is my acceptor impurity concentration. No? So this will be the number of free electrons. Okay, why N plus Na? N is your electron concentration. Now Na, no, sorry, mali ako. This is not the number of free electrons, no? This is the negative charge. This is the amount of negative charges. Okay. Why is it N plus Na? N is the number of free electrons, no, per cubic centimeter. Na is the number of acceptor impurities per cubic centimeter. No? But when your acceptor impurity is ionized, it will accept an electron and it will become negative. That is why when you have total ionization, Na becomes or contributes to the amount of negative charge inside your solid. So your negative charge inside your solid will consist of your free electrons or conducting electrons, and then the number of acceptor impurities which have accepted an electron and therefore became negative. In the same way, P plus Nd is your amount of positive charge. No? And if your semiconductor material is neutral, that means that N plus Na will be equal to P plus Nd. No, so there was a question earlier, is it possible for material to have both donor and acceptor impurities? Yes. No. So this is the case where you can have both. You can have Na and Nd both being not equal to 0. Now, we said that Np is equal to Ni squared. No? Now, itong Ni na to, this is usually constant at a fixed temperature. So in these two equations, I have 4 variables. What are these? No, I have N, P, Na, and Nd. And so if you know 2 values, you can solve for the other 2. So using these 2 equations, kung alam ko yung Ni and alam ko any 2 of these, I should be able to solve for the other 2. Okay, in your notes, there's a formula given for N and there's a formula given for P derived from these 2 equations. Now, I never showed that formula, or I never derived that formula for my class, ano? For my classes, because para sa akin, you just have to memorize these 2. in fact, you don't even have to memorize it, no? You can it's not something you have to memorize. No, you can just think about it. No? This is your total negative charges. This is your total positive charges. They should equate to each other. This is your mass action, no? And as long as you know and as long as you know 2 of any of these 4 variables, you can solve for the other 2. So anyway, that's just a tip for you. Are there any questions? Okay, by the way, there are some simplifying assumptions. No? Now, for example, if the donor impurity concentration is going to be very much greater than N, no? Then N will be approximately equal to, sorry, then Ni. Then N will be approximately equal to Nd. No? If your donor impurity concentration is very much greater than your intrinsic concentration, then N will be approximately equal to Nd. In the same way, if your acceptor impurity concentration is very much greater than Ni, then P will be approximately equal to Na. So this is similar to what we were saying earlier, bakit nineglect to, no? Okay. Bakit nineglect yan? That's because it's going to be, usually it's going to be very much smaller than Nd. And therefore your free electrons is just going to be approximately equal to Nd. Okay. Any questions? Okay, I'll speed up a bit, no? Number of things that I wanted to discuss. First is the Fermi function. It's important that you try to understand this because the Fermi energy level is going to be referred to later on when you study how a diode and a transistor operate. Now, the Fermi function f of E is the probability that an energy level or that an energy state, again, no confusion between energy state and with energy E, okay, if existent, no, I'm going to put that in quotes. I'll explain what I mean by that later on, is occupied by an electron. The probability that an energy state with energy E, if this state is existent, is occupied by an electron. So this is a probability function. What is the maximum value of a probability function? No? When the probability is 100%, the maximum value of the probability function is equal to 1. No? And the minimum value of a probability function would be equal to 0. So if I plot, let's say these are my possible energy states in my vertical axis, no? And this is my Fermi function in my horizontal axis. Let me show here EC and EV. Let's say this is an intrinsic semiconductor. Okay. This at 0 degrees Kelvin, my Fermi function is going to look this way. At 0 degrees Kelvin, my Fermi function is going to look this way. where the value of this energy we call EF. EF is what we call the Fermi energy level. Okay. Now, what is the significance of this? No? So this is the Fermi function f of E at 0 degrees Kelvin. We are saying that the probability that your energy states below EF at 0 degrees Kelvin is occupied is 1. No? The value of this is 1. And the probability that the energy states above EF at 0 degrees Kelvin is 0. Which is consistent with what we said about the valence band and the conduction band at 0 degrees Kelvin. No? Sabi natin, at 0 degrees Kelvin, lahat ng electrons dito or lahat ng energy states dito will be occupied. And at 0 degrees Kelvin, there will be no occupied energy states here in the conduction band. In fact, in other words, all the electrons will be here. There will be no electrons here. And that's why the probability here is 0 and the probability here is 1. No? Now note that you have a forbidden band. So in reality, there are no energy states between EC and EV. That's why I said here, if existent. No? If existent. Because between EC and EV, there are no energy states. No? So our energy states are really below EV and above EC. Okay, now what happens if I increase the temperature? My probability now will look like this. No? So the greater temperature, my probability will shift to look like this. So this is f of E at T greater than 0 degrees Kelvin. Okay. And the inflection point is going to be 1/2. No? In other words, we can redefine EF to be the probability that an energy state is occupied is 1/2. No, that is a little confusing, no? So this is when the probability that the energy state is occupied is 1/2, no? The probability that the energy state EF is occupied is 1/2. Of course, we know that there is no energy state between EC and EV, no? So EF is really just a theoretical value. But that is when the probability will be equal to 1/2. Okay, will there be electrons here? Will there be electrons here? No, because ang probability natin dito is 0, and the probability here is also still 0. So is also still 1. No? So there will be no electrons here, and all the holes here will still be occupied, no? Because your probability is 1. Now, what if I raise the temperature even further? No? So sabihin natin ito yung temperature ko ngayon. No? So magiging ganito yung graph ko. So this is a higher temperature. And then ngayon, makikita nyo na at this point, no, you can now have occupied energy levels. Hindi na ngayon 0 yung probability. No? The same way here, naging less than 1 yung probability. No? So ang ibig sabihin nito, holes will exist. Okay? So that is that is the significance of your Fermi level. So that dictates the probability. Now, mag-iiba yan if you have a dope semiconductor. No? So if you have, let's say, an N-type semiconductor, ano mangyayari? Okay, again, this is going to be EV. Let's say this is EC. Okay, I'm going to define a new variable here. I'll call it EI. EI is my intrinsic Fermi level. Your intrinsic Fermi level, that is the Fermi level of an intrinsic semiconductor. No? And in this particular case, EF, EI, no, EI, well, this is intrinsic, no? So in this particular case, EI is equal to EF, and EI is equal to 1/2 of EC plus EV. No? Sorry. Yeah, 1/2 of EC plus EV. That's assuming that the bottom of the valence band is our reference. So it's actually the average between EC and EV, or the midpoint between these two. So that is my intrinsic Fermi level. Now, if this is N-type, ang mangyayari, my Fermi level is going to be up here. This is going to be my Fermi level. In other words, even at 0 degrees Kelvin, sorry. At 0 degrees Kelvin, wala pa rin, ano? But let's say this is my inflection point. This is 1. Okay. Under normal circumstances, this is going to be my Fermi plot. Okay. So kahit na ang probability that all my valence electrons are occupied, meron pa rin akong electrons existing. In the conduction band. And that's despite the fact that all my valence electrons are occupied. No? The probability is 1. Okay. Samantalang sa P-type, the opposite will happen. This is my EI. My Fermi level is going to be here. Okay. So my inflection point will be here. Okay. So under normal circumstances, I might not have any electrons, but I will have holes. So you have holes existing. Why do I know that holes exist? Because the probability that this is occupied now will be less than 1. So if the probability that it's occupied is less than 1, that means that there are holes. No? Even if the probability that there are free electrons is equal to 0. No? Okay. Are there any questions with regard to this? Okay, I don't have time anymore to discuss the rest of the material for the module 1B. No? So I'll just give you a brief run through of what you should study. You know? So you should be studying the conduction mechanism, in semiconductors. Okay, so there are 3 mechanisms for movement of charges in semiconductors. The first is drift. The second is diffusion. And then the third is recombination and generation. Drift, this is movement of charge due to an electric field. No? Diffusion is movement of charge due to non-uniform concentration. Ito naman, recombination generation. Recombination is when electrons and holes combine to form a neutral particle. That's recombination. And generation is when electron-hole pairs are released because of some excitation. That excitation might be radiation or some other form of excitation. Okay, so those are the conduction mechanisms in semiconductors. I was going to go through both the drift and diffusion pero wala nang oras. So ganito na lang. Please study the material. If you have any questions, you can post them in Piazza, and I or some other hander is going to try to answer. If you want, for example, a supplemental session, no, like if you cannot understand something and you want it to be explained to you in person, get in touch with me and I'll see if I can accommodate you. Okay, so that's all for now. No, on Tuesday, I intend to go to yung third part of module 1 already, no, which is a discussion of PN junctions, and then subsequently we're going to be discussing bipolar junction transistor structure. Okay. Any questions? Sige, I'll as usual, I'll close the session as soon as everybody is gone. Okay. But again, please take a look at the material that is published. In fact, I also would suggest that before you go to the session, tignan na rin yung material that is published, because at least it might help you in understanding what I'm talking about. Okay. So thank you.
Thank you, sir.
Sir.
Thank you po, sir.
Thank you po, sir.
Thank you po, sir.
Thank you,
Welcome.
sir.
You're welcome.
Yes, sir.
Thank you po.
Sir, saan niyo
Yes.
po pala i-post yung videos ng mga sessions po?
Naka-post, no? I've been posting them.
Sa Ovle po, yung videos?
Hindi naka-post sa Ovle, but
Okay po.
I gave instruction in Ovle, pag gusto niyo hanapin yung video, pinost ko sa YouTube. You
Okay po. Yeah. I
look for
remember po pala.
E131 RVM, hanapin niyo, no?
Okay po. Thank you po.
Okay.
Thank you, sir.
You're welcome.
Sir, may itatanong lang po ako pag nilinaw lang po.
Sure, no problem. No
Doon
problem.
medyo hindi ko po iniisip ko po yung relation no yung N plus NA equals P plus ND doon sa mass action, no? Medyo hindi ko po ganong magets yung mass action, no?
Dalawang equations yun, they're completely independent of each other. Yung N plus NA,
For positive, for ano po yun, di ba?
yeah, that's the amount of negative charge, no?
Wherein yung N po doon, sir, yun po yung free electron, tama po ba?
Yes, so yung N plus NA, yung N plus NA, NA, no? So itong N na to is the concentration of free electrons, no? So each free electron has a negative charge, di ba?
Apo.
Okay. Ito naman, ito yung acceptor concentration. Acceptor concentration. Each acceptor, di ba may hole? May hole yung acceptor, di ba?
Apo.
Pag na-ionize yung acceptor, pag nakatanggap yung hole ng electron na yon, yung acceptor atom becomes negatively charged. Right? So ito, yung concentration of free electrons, each electron has a negative charge, no? Yung acceptor concentration, each acceptor because its hole will accept an electron will become negatively charged. So ito yung magiging total negative charge. And that should equal the total positive charge, which is P plus ND. No? Kasi P is your concentration of holes. Each hole is effectively positively charged kasi kulang ng electron eh. Kung kulang ng electron, nagiging positive siya, no? Ito naman, yung ND, each donor mawawalan ng electron kasi yung electron ng donor pupunta sa iba. So magiging positively charged din yung impurity. So this is your total positive charge, this is your total negative charge. So dapat equal silang dalawa kasi yung solid natin, sabi natin, is neutral, no? Now, iba pa yung mass action, no? Yung mass action is if you multiply N by P, that will always give you Ni squared. So this is the same N. Itong N na to, yun din yung N na yan. Itong P na to, that's also this P. So N is your total free electrons, P is your total holes. That will always be equal to Ni squared. Kahit na intrinsic, kahit na extrinsic, it will always be equal to Ni squared. And then I explained why, di ba? Kasi pag for example, intrinsic, pag pure, dinagdagan mo ng donors, lalaki yung N, mas malaki yung probability na mababawasan yung holes dahil yung ibang electrons pupunta dun sa mga holes, so mababawasan yung P. So habang linalakihan mo yung N, nababawasan din yung P. Kaya nagiging constant yung product nila ng dalawa.
Oh, okay, sir.
Okay, so iba ito kaysa dito, no? They're not related to each other.
Iniisip ko ba baka ako may connection silang dalawa? Kaya yun na lang.
Walang connection. This is neutrality. This is neutrality. Ito naman, this is yung mass action law, no? That the product of your free electrons and holes will always be equal to a constant.
Okay.
And then pag alam mo itong dalawang to, pag given any two unknowns, no? Any two unknowns or any two givens, masosolve mo for the other unknowns. No? Kasi dun sa notes, no? Pag tinignan mo yung notes, may binibigay yung notes na N is equal to ND minus NA
Yan nga
over
po, sir.
plus the square root of blah 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 blah. No, I don't know if you saw that. That's somewhere in your notes.
Doon po ako ngayon, sir. Medyo nalilito din po ako.
Okay. What I'm telling you is, kung ako lang, I wouldn't care about this, no? Kasi kung alam mo to, at saka alam mo to, then you can solve your problem. You don't have to apply this formula. Because this formula was just derived from these two. No? And yung mga calculators natin ngayon, it's very easy to solve even nonlinear problems, no?
Opo.
Kasi yung mga calculator natin may solve function eh.
Opo.
So,
Nagsalba sa amin, sir.
okay. So siguro ito dinederive ng mga libro dati kasi walang mga solve function yung calculator, no? But kung alam mo tong formula to at saka alam mo tong formula to, it's very easy to use your calculator now to solve for your unknowns.
Okay po, sir. Tapos, sir, dun po sa total ionization, Tama po ba na nawawala doon yung excess na electron?
Hindi, ang ibig lang sabihin ng total ionization, for example, kung Na, that is your number of acceptor impurities, ang assumption natin, lahat niyan tatanggap ng electron. Di ba? Kasi these are holes no? Ito may butas na to di ba? For example, boron, no? 3 lang siya. So may isang butas. Of course may katabi to, no? May mga katabihan, no? Galing sa mga katabing atoms, pero boron naturally may butas siya, no? May hole. This is a naturally occurring hole. No? Pag sinabi nating total ionization, ang assumption natin, there will be some electron somewhere that will occupy this hole.
For hole lang po siya, sir, or kaano din po siya dun sa ND, wherein sa ND, ano po yung mangyayari dun sa excess electron po?
Hindi. Pag occupied na ito ng hole, wala na, ionized na siya. No? What do you mean by anong mangyayari sa ND?
So ang total ionization po, sir, parang for, ano lang siya, for acceptor.
No. Also for donor, no? Pag ND naman, ang assumption natin, kasi ND, di ba, may extra, no?
Excess pa.
May excess. So, after all the covalent bond, meron pa siya isang extra na gano'n, no? Ang assumption natin na ito will go to the conduction band. Yun ang ibig sabihin ng total ionization. Pag hole, lahat ng hole malalagyan ng electron, no? Pag ND naman, lahat ng free electron niya aakyat dun sa conduction band. So yun yung ibig sabihin ng total ionization. In other words, walang electron sa impurity na hindi aakyat, no? Lahat sila aakyat dun sa conduction band.
Okay po, sir. Siguro, sir, last na po ito. Dun
No
po
problem, no problem.
Dun po sa pag-akyat, bakit po sila umaakyat? I mean, excess na sila, gano'n, sobra na sila.
When I say akyat, hindi physical akyat yan, ha?
Okay po.
Okay? Hindi physical akyat yan, ha? Ang ibig ko lang sabihin na akyat is it has now enough energy na pwede siyang lumibot kung saan kahit saan sa solid, no? Kasi
Okay po.
kasi there are two types of electrons. Yung isang electron tinatawag nating bound, no? Yung isang electron tinatawag nating free, no? Pag sinabi nating bound, ibig sabihin malakas yung kapit ng nucleus sa kanya, no? Yung kinakapitan talaga siya ng nucleus, okay? Na hindi siya makagalaw.
Okay.
Pag sinabi nating free, ibig sabihin hindi na siya mahawakan ng nucleus, no?
Makulit na po siya.
It has enough energy na nakakalibot na siya kung
Opo.
saan-saan, no? So, pag sinabi kong akyat, baka ang impression mo is physically may parang layer sa taas.
May layer
No.
po ako sa taas.
Hindi ganoon, ano?
Ganun pa rin po siya din, bro.
Think of it conceptually, no? The electrons can be very near each other, no? Yung electron, yung bound electron at saka yung free electron, pwedeng magkalapit lang sila. Pero yung isa hindi makagalaw, parang ano siya, kapit na kapit yung nucleus sa kanya. Yung isa naman, pwede akong gumalaw-galaw kasi malakas yung energy ko, no? But they can be in the same area.
Okay po, sir. Ito po, sir. Sorry, last na po tayo.
No. Okay lang.
Yung doon po sa acceptor concentration tsaka donor concentration, meron po ba tayo doong specific value? Yun po ba yung sinabi nyo kanina na
Typical value yung sinabi ko.
yung 10 raised to 15 impurities po
Yeah.
doon sa ND? Tama po ba?
Yeah, this is typical.
So yan po, sir, for NA, or for ND lang po ba siya or for NA din?
Typical for both NA and ND.
Okay, okay po, sir.
Pero pag binigyan ka naman ng problem, usually sasabihin sa iyo what is the value of NA and what is the value of ND, no?
Tas po doon na po yung sinasabi niyo na as long as alam niyo yung value ng isa diyan sa dalawang
No,
parte na yan.
yung if you know the value of 2 out of the 4, no, and then alam din niyo yung value ng NI, masosolve niyo yung problem, no? By the way, no, I hope hindi ka malito, no, but yung NA at saka yung ND hindi pwedeng indiscriminately gawin mong malaki, no? Kasi meron tayong tinatawag na degenerate, makikita nyo to sa notes, no? Degenerate doping. Na pag masyadong malaki na yung doping concentration, it will not behave anymore like a semiconductor. It will start behaving like a metal. Pag masyado mong dinagdagan ng charge carriers. Medyo hindi na siya nagiging, it does not behave anymore like a semiconductor, no? It will start behaving almost like a metal. So yung doping, may maximum limit yan na hindi, na semiconductor pa rin yung magiging behavior niya.
Yun po yung sir, 10 raised to 18.
Something like that, no? Something like if it's greater than 10 to the 20, or baka tama ka, baka 10 to the 18, no? Hindi ko na maalala yung exact number.
Ayun po. Yun lang naman po, sir, ang sa akin. Thank you very much po, sir. Sorry po, sa dami ng tanong.
No. I appreciate it. No. If you really have any questions na gusto mong malinawan, I'm free to discuss at the end of the class, ano? Basta't wala akong appointment after. You can take up my time anytime.
Sige po, sir. Thank you very much po, sir.
Sige.
Bye po.
Thank you po.
You're welcome.
Bye.
You're welcome.